Hi, and welcome to the Amphenol webinar series. Harsh Patel, Amphenol Senior Field Application Engineer, will present an automotive high-speed signal protocols and standards webinar. If you have any questions throughout the webinar, please hold them to the end. You can type them in the questions section or raise your hand, and when the presentation is over, we will answer your questions. Thank you.
All right, thank you, Lori. Hello, good morning, good afternoon, good evening, everyone, from wherever you are. Thank you all for joining today's session. And my name is Harsh Patel. I'm a senior FAE for the automotive markets for Amphenol ICC. My educational background is in electrical engineering, currently pursuing my EMBA. I was a signal integrity engineering supervisor at Molex in my previous role. And before that, I have some experience in video broadcast, semiconductor world as well. And in today's webinar, we're going to be focusing on automotive high-speed signal protocols and standards. And we're going to be keeping it pretty high level so everyone can understand the content from various educational and industry backgrounds. So let's get started. So as you might already have seen or heard from a variety of spots like CES show, for example, that just happened, right? There's a lot of great activity happening in automotive, and the goals that everyone has in terms of companies and suppliers, tiers towards full autonomy, right? So this is a high-level overview of where we were about 10 years ago and where we are now and where we're headed in terms of all the connections we have for high-speed signaling in cars for various applications such as cameras, gateways, ADAS, autonomous driving, connected car, and etc. And it's no surprise that we're exponentially growing in the number of ports or connections we have in a vehicle. So with all the new features we're seeing in cars today, we're getting closer and closer to that full autonomy, right? You can notice in another 4 or 5 years, we're looking at over 100 ports for these applications and moving us closer to that level 5 autonomy. I'm talking about the levels of autonomy a little here, but in the next slide, I actually go into some detail. So if you don't know what that means, don't worry just yet. We can dig a little bit deeper into that just in a little bit. But if you look at where we were in 2008 with 1 port and where we are today, probably between 10 and 100 ports, right? We're significantly, I would say, exponentially increasing in the number of ports that we have in a vehicle. So this is a really nice summary that SAE has done on levels of driving autonomy and automation. So they've done a good job with the questions on the left. So, what does the human in the driver's seat have to do? What do these features do? And then, example features for better understanding. So they, at the top, you see level 0, 1, 2, 3, 4, 5. So 0 being there's no automation, driver is absolutely required, and level 5 being the complete opposite, right? Full automation, where the driver is pretty much not required to do any driving at all, and the car is pretty much autonomous at that point. So, in between is where you have, driver assistance, for example, level 1. There's some features that provide support to the driver. You have level 2, where is, partial automation. You have some features that actually support the driver, such as lane centering and adaptive cruise control. You got level 3, which operates unless required. Basically there's features that help the vehicle drive in limited conditions. Level 4, which is high automation, this is where it starts to kind of get to the point where you might start to see the pedals or the steering wheels may or may not be installed. And then obviously, level 5, full autonomous, you're definitely going to probably have a vehicle that looks something like the right side here. So no steering wheel anymore. It's just, passengers and the car will drive by itself, right, at that point. So and this picture is an interesting one. I actually found this really interesting when I first heard about it a while back. Did you know that the third heaviest component in a car is actually all the wiring harnesses combined together? and it's actually third behind the engine and the chassis, respectively. So it totally makes sense from the trend that we just saw a couple of slides ago, right? And the increase in the number of ports we have, and all the features that are increasing in a vehicle. This is, absolutely amazing for someone like us, but also in the industry in general, right? Automotive suppliers at all different areas are going to see this increase in, modules, whoever deals with gateways and things like that as well. So I got this a picture actually from a really nice white paper from IXIA, and they wrote a paper on automotive Ethernet if you'd like to check out more on that. This one is really interesting actually, and it was presented at Automotive Ethernet Congress in 2019 by Kirsten Matthews from BMW. And I really like this to show just how many different networking technologies there are in a vehicle, right? So this has all the low speed stuff, for example, the CAN and the most, 25 FlexRay, and those protocols, as well as the high speed, such as the Automotive Ethernet and LVDS and whatnot. So in today's presentation, I'm going to actually focus more on the high speed stuff in the coming slides. And there's a lot of things on here and it's kind of overwhelming, but just understand that, not everything is, in a vehicle per se, as we see, on the screen here. It's a high level overview containing, all pretty much, even including the alternatives at times, right? So some of these are, this or that, right? Not both. And oftentimes OEMs actually have choices. So they're going to design and implement, depending on what their needs are. And there may be some advantages and disadvantages between the choices they have, right? So yeah, that's kind of, where this comes from. And this is a really nice chart, just kind of goes over the bit rate on the y-axis and years of appearance, like when it started to come about. So you can kind of see the automotive Ethernet stuff in 2020 and beyond. So okay. So there's a lot of different high-speed signal protocols and standards out there, created for a variety of applications or use cases over the years in automotive. What I'm going to do today is break them up at a high level and explain a little about them to get you guys familiarized with it. So knowing and understanding these groups is pretty much, separated by, LVDS or ASA, for example, Automotive Ethernet, and so on. And that's going to help you understand automotive a little bit better too. So in all these various specs and standards, there's two main aspects that we must focus on, right? And from just a requirement standpoint. So the two are basically SI requirements, where things like for the channel, you're going to talk about insertion loss, return loss, mode conversion, impedance, intra-pair skew, inter-pair skew, crosstalk such as near end, far end, and etc. Right? So those are the SI requirements. These are all parameters that look at different things for the signal to see pretty much the integrity of the signal, right? Going from point A to B, and you want obviously 100% ideally, but there are realistic real-world problems that restrict it. So that's where all these parameters come into play to basically gauge what type of signal we get at the receiver side. And then you have EMI/EMC requirements, looking at two main requirements, right? If you look at EMI/EMC, so one is to ensure that systems must not emit excessive electromagnetic interference, EMI, or noise, and the other must be to be immune to the noise emitted by other systems nearby, right? As you know, in a vehicle, there's going to be various things going on in the harnesses as well as nearby systems. So some of the parameters that we look at from a cable assembly of a connector standpoint, from a connector standpoint, for EMI/EMC are the following, and they are, screening attenuation, coupling attenuation, transfer impedance, and etc. So as we get faster and faster in automotive with respect to data rates, the EMI/EMC is getting very important. And there's a lot of focus on it from a design standpoint, and it's actually become very critical in standards activity as well. So these are some of the areas that we must focus on a lot as we kind of increase this, data rates. And you'll kind of shortly see as we, take a deep dive into automotive Ethernet and such, right? That the data rates we're talking about now in automotive is, significantly increasing. And we're almost catching up to datacom, you can say. So on top of these requirements, pretty much everyone knows that in automotive, there's going to be a pretty big consideration of environment requirements as well, and testing as per the OEM specs or industry standards like US CAR and LV214 and etc. Right? So these environment requirements are things like shock and vibe, thermal aging, humidity, and etc. that the cables and connector must pass through each requirement, and pretty much the SI requirements have to still meet, right, even after going through environment conditioning. So that's kind of the background and high level understanding of that. So now what we'll do is we'll go through kind of each of these areas that we just discussed and take a deeper dive so we understand a little bit further. So first one I'd like to kind of talk about is LVDS, which stands for low voltage differential signaling, and GVIF, which is a proprietary protocol by Sony, and it stands for gigabit video interface. I've kind of lumped them together here on this slide because the application or use case they support, it kind of fits together. They both pretty much deal with, displays and video applications. And then we have ASA, which is a standards body that actually stands for Automotive SerDes Alliance. It was founded pretty recently in 2019 with a key interest from BMW, Continental, Broadcom, Fraunhofer, and NXP. And these companies, and now a whole lot more actually, members have joined since then to basically move towards standardizing the asymmetric SerDes for high-speed P2P communications in vehicles. So, now that the high level overview on those three kind of we did, right? I want to mention like a few chipsets for each one, right? So LVDS has been a long, they're pretty long term now, and there's been generations of TI or Maxim and Innova chipsets, and so these are FPD links 1, 2, 3, 4, and so on, right? And these are proprietary links, and why I'm mentioning those is, with respect to the requirements that we mentioned earlier, the SI requirements, right? There's something called like a chipset channel requirements document, right? That we would kind of need for each of these, SerDes. And what that chipset document actually entails of is it goes into detail of what the channel must perform to in terms of the SI requirements that we discussed earlier. And in order for the chipset to work as it's intended, right? So that's kind of the background on how we deal with chipset documents. And obviously the OEMs or the tiers have a preference choice, and they will pick whatever one, and we will have to look into the details of the chipset channel requirements and understand what type of requirements it means for the channel from our standpoint. Some major advantages of LVDS are that it's low power consumption, simple cabling and termination, low supply voltages, and it's high interference immunity that it has. So kind of going in the future, we can kind of see ASA is being worked on right now in the committee, and there's a lot of participation and involvement from a lot of different companies there. And standardizing ASA, it pretty much means that it's going to be interesting to see what these big companies like TI, Maxim, and Innova do, but it pretty much means that there's going to be a competition between the proprietary links that we've seen thus far, and once it's standardized, there's going to be obviously new players maybe that arise, or it might be the some of the old players also playing in the ASA space. So it's going to be interesting to see, and this is a common theme, as you'll see on the next slide, that in automotive right now, there's a lot of different standards activities going on, And there were some that started and kind of merged with another and whatnot. So yeah, there's just a lot of uncertainty at this point, and it's hard to say which one is going to be a clear winner for certain applications, right? But let's continue on to talk about automotive Ethernet. And this is a big one. If you take anything out of today's webinar, it'd be you know, automotive Ethernet. It's pretty big in terms of you know, just the trend that we're seeing. That's common agreement between all the you know, players in the automotive market. And so there are two big standards bodies when it comes to Ethernet, right? One is IEEE that you guys have probably heard about from, you know, Datacom or other industry, and Open Alliance, which basically takes the work done in IEEE and uses that information and the baseline for full channel, and tries to basically figure out the limits of components such as cable only, connector only, and etc., and defines the testing setup and equipment settings and etc. too. So it kind of makes, you know, everyone test and evaluate the cable assemblies or whatever component we're talking about in the same way. So some of the big automotive you know, specs out there are basically 100 base T1, which is 100 meg spec, which is also known as 802.3 BW, also known as 100 M automotive Ethernet, or broader reach from Open Alliance, right? All of that basically means the same thing. We're referring to the same spec. So I actually put all of them just as a reference. So, you know, if you hear any one of those, it means the same thing, right? So it's good as a reference. And then you have 1000 base T1, which is, you know, exactly what it seems like. It's 1 gig 802.3 BP or 1 gig automotive Ethernet. Or in Open Alliance, we actually have two specs. So it's, you know, unshielded twisted pair, UTP, and then STP, which is shielded twisted pair. And it's also known as 1000 base T1. So yeah, these specs, you know, the UTP, STP, there's two versions. They're slightly different. There's a few parameters that are updated or changed just because, you know, it doesn't apply to unshielded, for example. And the shielding one, we had to add in the shielding parameters. So yeah, some of those updates are there, and that kind of defer the two specs. You also have the 10 base T1, which is a technology that was created for basically multi-drop network, which can be used in application kind of currently that's using CAN FD, FlexRay, or even 100 base T1 today. So some of the benefits, you know, for that one is, you know, no switches, less cables, up to 8 nodes you can have, and go about at least 25 meters. And then the 10 base T1L actually stands for long, and the length that we're talking about there can be extended up to, I think, 1 kilometer long cables. And then right now, just the most recent completed spec was the 2.5, 5 gig, and 10 gig, which is known as the multi-gig Ethernet spec. It's 802.3CH. That one finished, I think, last year, and so yeah, now we should actually, you know, start to see a lot of implementation in that area, and probably work going on right now as we speak, and we'll probably see it in vehicles 2 to 3 years from now. And then currently we're working on automotive Ethernet 10 gigs and beyond, which would be 25 gigs, 50 gigs, and 100 gigs. And it's referenced as 802.3CY, or greater than 10 gigabits per second automotive Ethernet. And so yeah, this is the current work going on right now. In Open Alliance, we're actually working on the multi-gig spec. So Open Alliance kind of lags a little bit in time frame, right? Because once the IEEE spec is complete, that's when Open Alliance kind of starts the work, right? So yeah, a little bit lagged, but that's kind of the overview on automotive Ethernet. All right, and then I have various others, and there's a long list of different specs out there, and this may not even be everything, but these are some of the big ones that we would probably hear in automotive the most. So A2B is a daisy-chained, single twisted pair bidirectional data bus. And it's ideal for supporting multiple channel audio with no jitter, extremely low latency, such as 50 microsecond. And in terms of data rate or bandwidth, we're talking about like 50 megabits per second bandwidth. We have DisplayPort, which is part of the VESA, Video Electronic Standards Association. It's an international standards body that sets industry-wide interface for the PC, workstation, and consumer electronics. And specifically in automotive, DisplayPort is widely used for like display applications in a vehicle. We have MIPI, which is Mobile Industry Processor Interface. MIPI is actually something that interfaces with high resolution cameras, lidars, radar sensors, information control, entertainment displays, telematics hubs and audio systems, data storage, wireless chipsets, right? Cellular, Wi-Fi, Bluetooth, and GPS. So pretty much a wide variety of things there. And similarly, HD-base-T is a global standard for distribution of ultra-high definition video, audio, Ethernet, controls, USB, and even upwards of, I think, 100 watt of power over a single cable. So that's kind of a unique one, and you can kind of see the benefits of that. And goes up to, I think, 100 meters. And HD-base-T eliminates, cable clutter because it's going over one single cable without compromising the performance or the high quality. And some of the board members there for HD-base-T are LG, Samsung, Sony, and Valens. And then we got PCIe, which you probably heard of from Datacom if you have that background, or other places. But this one I'm referring to is specifically to automotive. It's starting to we start to hear more and more about this because of some of the benefits PCIe has, right? So there's now a special group in automotive for PCIe as well. And in automotive applications that require like really low latency, so 1 to 100 nanosecond range, this option is coming up more and more. And the reason is, the point-to-point link dedicated to each device, short cables. These are fairly short, I think shorter than a meter, half a meter type thing. And then we have our USB, so 2.0 and 3.x. So this has been there a really long time in automotive. It's part of the USB-IF standard, and USB ports in vehicles today, things like charging your phone or plugging in a USB for music and etc. are widely used, right? So we still see those today. And these are, just some of the other various other things like industry standards that we mentioned. And some of these are actually like, based on the description, you probably understood like they're kind of doing the same thing, but obviously it's a different standard, different signal protocol. So there is going to be competition and there is going to be choice for the final system implementation. So this is where it's kind of hard to predict which one is going to be the clear winner. But as the OEMs start to implement this, we will probably start to figure it out in the next few years now. But in the last maybe 2-3 years, I would say there's been a lot of new standards work committees that have begun, and that's where the kind of uncertainty comes from. So this is a nice picture from the CFI from IEEE on the 10 gig beyond consensus building presentation. This is a nice one to show where we are currently with our EE automotive architecture, and it's pretty much reached its scalability limits, right? So the zonal architecture brings forward 2 new devices, vehicle server and gateways, that reduces the number of ECUs that we use in a vehicle. It enables us to use Ethernet and a variety of flexible and hybrid topologies. So in automotive, the transition from domain to zonal, it's already started, and it's happening in stages at various OEMs, and they're all at different progress with it, right? So by moving to zonal though, like it's allowing them to reduce the hardware components and wiring, which we saw in the picture. It's obviously, on an exponential rise. So weight is a big concern, and therefore, obviously, reducing the hardware components and making things less weight, overall cost reduction, that's where it's going to come from. So it's become a very important topic for the OEMs, obviously. And just wanted to take a moment here and define gateway as well. So for those of you that might not know, it's similar to datacom, where it acts as a local connectivity hub, relaying data through a single high-speed Ethernet link to the backbone. Okay, and then these are justifications that were given in that same CFI that I mentioned earlier in IEEE Automotive 10 gigs and beyond. So when we were trying to propose 25, 50, and 100 gigs, these were some of the reasons, and these are really interesting, and it kind of shows where we're headed and what kind of things we're thinking about that will require these type of data rates or bandwidth, right? So I wanted to share that. I think that will give you a nice perspective as to why, like the why behind some of these data rates. Because if you were just to look at 5 years ago or maybe before that, we were still talking about 480 megabits per second USB type of signals, and now we're talking about something similar to what we talk about in datacom, right? So it's a big jump, and yeah, maybe it's hard to understand. So some of these reasons we'll go over today. So transition of us moving from a traditional architecture to zonal architecture is going to require 10 gigs and beyond links between the zonal ECUs or gateways that I mentioned, right? So that obviously means that we need higher data rates. And then you're also going to start to think about redundancy, right? So in processing units that are required to enable autonomous cars, there's going to be more and more bandwidth required there, obviously, because we're having two of everything, right? This is more important because these processing units that I'm referring to are actually going to be controlling the vehicle or making decisions that affect safety of the passengers in the vehicle, which means obviously redundancy is required when we start talking about ASIL ratings and such, right? So, and for example, like in my car, I know that the steering wheel is drive-by-wire. It's like a 3-tier failure redundancy system. So just similar to that, each of these, redundancies in like chips or PHYs are going to be there as well. That requires more and more bandwidth. Another key bandwidth-related item comes from autonomous driving systems is that sensors and other like cameras and such, right, that actually collect uncompressed data, which will have to be transmitted and received from one switch to another or to the nearest gateway and vice versa at a really fast rate, because some of this compressed or uncompressed data is actually used to make decisions. So that's going to be another reason. And then you have probably heard of a black box in a plane, right? So something similar is going to be there in autonomous vehicles, and that's going to mean that there's going to be a significant amount of bandwidth required. Obviously, that we're going to be storing this data somewhere, right? Raw sensor data on the vehicle in case of accidents or anything like that, right? So we still don't know how insurance is going to play into all this, but I think that's where some of these features are being discussed for. And then just to give a reference, this is probably outdated now, but at that time we were estimating roughly 4 terabytes of data would be collected by a single autonomous vehicle per day. And I think if we look at numbers today, it's probably significantly higher than that, because from that time to now, I think we've come a long way, and we're adding more and more components, right, and sensors and things that probably adds a little bit of data compared to what we were estimating back then. So yeah, that's one of the other reasons. And then the last reason is at the time OEMs were actually already using, because they were trying to get to their future, levels of autonomy. They were actually using enterprise class Ethernet devices for the 25 gig and 50 gig, just for lab level tests and stuff, right? But that was another good reason why we needed a specific spec for Ethernet automotive that was, at those data rates, right? So 25, 50, and 100 gigs. So that's kind of where that came up as a requirement. So these were some of the justifications to why we were heading that way to the higher data rates. And then these are challenges. So from all of this, you probably already kind of understood, right? Some of the challenges we have in standards work, some of the uncertainties, but I want to kind of go over these four that are very important in my opinion. So you have EMI that we discussed, and I kind of mentioned it earlier too, right? But you saw the image of the wire harnesses early on in the slide deck. You saw the increase in all the features and technologies we have in the vehicle today, where we're headed. So we're basically keeping the space of the vehicle pretty much constant, and we're adding a whole lot of cable and other components to make all these smart features for autonomy and EV, right? So the limited physical space available in the body of a vehicle um, kind of increases the possibility of EMI more so than what we've dealt with in the past. And on top of that, we're also increasing the speed pretty exponentially, right? So with this many components in close proximity to one another, the data networks must be, designed in such a way to both resist kind of the electromagnetic noise that could potentially be, thrown off by other components, and refrain from emitting those noises themselves, right? So design is going to be pretty key here, and kind of considering this early on in the design phase, what type of devices you're using, the interoperability with other devices, all that will be, like more important than ever before. Because before we really didn't look at this, I guess early on, we were looking at it, almost at the near the end of the design phases where everything kind of comes together. We do a CISPR 25 system level test, and that's where we would understand EMI, right? But I think some of these activities will start to, work differently, where we start to look at all this early on in the design phases. Or we have to consider them. Otherwise, there's going to be pretty big design risks and chances of failures, right? That will pretty much catch at a moment where we can't really do much with it. Another one is latency sensitivity. So this is another challenge that's definitely going to come up more and more in the standards work, and that's latency. So if there's a lag or a delay in the data coming from one of the sensors, it may be more difficult to fuse that data with another sensor where we were supposed to get a real-time image or something like that, right? A bird eye view, for example, that's a good one. And this is going to affect the decision making at higher levels of automation or autonomy. So, now more than ever, it's really important for the data to be sent and received from point A to B in a timely manner. And because we're moving closer and closer to that full autonomy, the human life is at risk, right? So some of these applications, because the links are kind of making decisions to stop the vehicle or pull over and whatnot, right, are getting very critical in that sense. And that kind of goes, hand in hand with the handling failures safely. So as we get to that full autonomy, handling failures safely becomes quite important. Highly automated vehicles must be able to recover from failures in a controlled way, like pulling over safely and whatnot. But better yet, we need to figure out ways that we can detect the failures before they even happen, right? That would be the ideal situation. And so a data network solution should be capable of rerouting around failures to ensure that the vehicles continue to operate safely until it comes to a stop. So this hasn't been the case in the past so much because, our links were kind of, related to infotainment and whatnot, right? Not controlling the vehicles per se. So it wasn't as critical. But now more than ever, these new requirements, will start coming in from ASIL ratings, and it's going to trickle down to the cables, connectors, and even other devices, right? Which is not so common, or hasn't been so common in the past, but this will be something that will come up in pretty much all the levels, right? Tiers in automotive. And we touched on this a little bit before, but weight is going to be another one. We're going to see the boom in features and move towards autonomy means that we're going to get more and more components, and that's going to mean obviously increasing the weight in the vehicle. And every gram of weight is going to be very important to the OEMs, and figure out ways how we can remove that weight as much as possible to make the vehicles more efficient, potentially reducing cost, right? So this will mean that some of the architectural changes that we discussed are gonna pretty much go into effect and start happening really quickly now in the next few years. And wiring that occupies less space, frees up room for other components, is gonna start to become a trend as well. So That's where the architectural changes will help, because the lengths of the cables and harnesses that we saw is going to significantly reduce, having shorter paths to the nearby ECUs or gateways. So this is kind of where these main 4 challenges come up in standards work, in automotive in general. But these are going to be very important for us to consider in every single thing we talk about in automotive, right? Design-wise, standards, requirements, our own designs for components, or everything in general. So, and I think that's all I had for you guys today. So thank you so much for your attention. And I'd like to open it up for any questions, comments that you may have. And my email's there if you have anything afterwards as well. So I think, Lori, you're going to open it up for questions, right?
Yeah. Yes. Hold on 1 second. I'm going to look to see. We didn't have any questions in the question list, but Dave Spencer, did you have a question? No. If you have a question, you can raise your hand or you can type it in the question box. I don't see anything at this time.
Okay. That was an easy audience.
Hold on 1 second. We do have one question.
Sure.
Where can we find automotive products online?
Yeah, so that's a good question. If you just head to our website, I should have put that in here, but yeah, I'll put that in I'll update the slides before they go out. But if you just head to our website, you can search by applications, you can search by the industry or whatever you're looking at specifically. So yeah, like if you're looking at specific applications such as, let's say, a USB connector for a USB 2.0 or an LVDS high-speed connector, right? You should be able to search based on the application and get to where you need to. And obviously, if you reach out to one of us, we can also address those needs that you may have and recommend something exactly with what you need.
Great. That was the only question that we had.
Okay, perfect.
Thank you everyone for joining the webinar. If it will be available on demand, and I will send the link to everyone who registered for this webinar. Thank you.
Thank you, everyone. Bye.